Alright everyone, what's up? Thank you for accommodating me as I travel to my conference on Friday. So here are the things that I need you to do for me. First, you'll find in the announcement that I sent out a Shark Tank video. And so I want you to watch that and answer quiz question 1. And that question is going to be about long run average total cost curves again, like we did with the Daisy Cakes example in class. Then I want you to finish your worksheet. So you'll recall that we did the tennis ball game, and as a part of that tennis ball game I had you all figure out some total cost, fixed cost, and variable cost at the very last time we used this worksheet. I want you to go back and plot total cost, fixed cost, and variable cost, and you'll see that they should look like the curves that we talked about, and then you're going to find which, based on your all's data, which quantity maximizes profit. And so go ahead and fill out the table down at the bottom of the worksheet and see if you can identify the quantity of balls that we should produce to maximize profit. Once you've done that, you'll go over to the quiz and answer quiz question 2 about that portion of the workshop. And then finally come back to this video where I'm going to do a little lecture on how we're going to represent profits graphically and what exactly the result that you found in the workshop means. I'll provide some more context there. If you don't have the worksheet and you don't have the data, I've uploaded it into our contents folder so you can download that worksheet, and I've provided you the data as well. Okay. So, when we plot total cost, it looks something like this, right? Typical total cost curve increasing at a decreasing rate, and then costs start to explode in the short run as we're perhaps running out of space in our factory or whatever we're operating in. In the workshop, you all plotted a total revenue curve. So total revenue equals P times Q. And so if you plotted that thing, it probably looked something like this. One thing to notice is we have dollars on the y-axis. Total revenue is in dollars. And so this function is basically Q with a slope of P, right? So it's just a line. And so if you're a firm thinking about the right quantity to produce to maximize profit, the question is, well, what quantity should I produce? And so that's what we're going to be thinking about in this little mini lecture here. Well, we know profit equals total revenue minus total cost. And so if we look at our graph, here's our total revenue curve, and here's our total cost curve. We want to choose the quantity that maximizes the difference between the revenues we bring in and the cost we pay out. And so it's pretty easy to see on here where it's not. Well, down here below Q naught, we notice that total costs are above total revenues for every possible quantity we can choose. So that's not good, because we're going to make losses if we produce down there. As we continue to produce, however, profits can grow. And so once we cross this Q naught here, we notice that revenue is above total costs. But what's the best quantity? Well, we might want to pick something where the distance between the two curves looks the biggest. So let's consider 3 quantities. Let's call this one Q1. Let's call this one here Q2. And this one way up here, Q3. So what we notice about profits at each one of these is that only one of them is the biggest. And so if we look at this vertical distance that I've drawn in here, that represents profit, right? At the quantity of 1, if we go up and hit the total revenue curve, that gives me total revenue. And if I use that quantity to bounce off my total cost curve, there's total cost. And so if we take the difference between those two, we get profit, right? Well, the question is, all right, if I'm producing Q1, can I change that quantity and make more profits? And you would see, well, yeah. If I produce more, that distance gets bigger. Total revenue gets higher than total cost. So we're going to produce more. Well, let's get to Q2. And then with Q2, we have profits of this size. So the question becomes, well, can I change quantity to make more profits, right? We're going to think about maximizing profits. Well, what happens to the firm when they produce Q3? When they choose to produce more at Q2? This distance gets smaller, right? Profit starts to shrink again. So it seems to suggest that firms can produce too little, right? And they could sell more goods and make more revenue and turn more profits. However, it also suggests that firms can produce too much. So why would profits go down if I keep producing up to Q3? Well, costs are exploding, right? It's that tension, that short-run tension that's created when the marginal product of labor starts falling and costs start exploding, right? We learned that earlier. So this is going to be what we call our profit maximizing quantity, Q star. Okay, you might want to redraw this graph. I'm just going to erase here some of these lines to clear it up. Well, just like we had sort of an equation characterizing the optimum for consumer choice when consumers are maximizing utility, we have the same sort of idea for profit maximization for firms. And so there's an easier way to figure out which quantity to choose than to draw a whole graph of data and figure out where the gap's going to be the biggest. And you all solved this actually on question number 11 on your workshop. And so the thing to notice is that at Q1, marginal revenue is greater than marginal cost. Now what is marginal revenue? It's just like we learned with marginal cost, the change in total revenue over the change in quantity. Whenever you see that word marginal, we're thinking about a change here. And then change in total cost over change in quantity is marginal cost. So if we wanted to put those on our graphs, this represents our slope of total revenue, and this represents our slope of total cost at quantity 1. And so what does this mean in words for marginal revenue to be bigger than marginal cost? It means that producing one more unit adds more to revenues than it adds to costs. Would you produce another unit if it added more to revenues than it did to costs? For example, at your lemonade stand, you can sell an additional lemonade for $1 and it costs you 50 cents to make it. Would you produce that? Yeah, that's going to increase your profits. Produce and sell that good. Down on this portion of the graph, at those lower quantities, we're adding more to revenue than we are to costs, and so we're absolutely going to keep producing. So what about Q3? Why doesn't Q3 represent an equilibrium? And remember what we talked about with equilibrium. At an equilibrium, there's no incentive for the decision maker to change their actions. And so, why is there an incentive for the firm to do something different than choose Q3? Why isn't Q3 the optimal choice for profit maximization? Well, if we look at Q3, we see that marginal revenue is less than marginal cost. Let's draw that up here. There's our marginal revenue at 3, and so I'll label that 1. And then here is total cost, or marginal cost at quantity 3. So we see that costs are growing faster than revenues. Why does the firm want to produce this good then? Well, one more unit adds more to total costs than to revenues. This is like you selling an additional unit of lemonade for 40 cents when it costs you 50 cents to make it. Your total profits are going to begin shrinking if you're going to take on those losses per unit. So the firm's not going to choose Q3. In fact, they're going to move the other direction. Let's reduce costs, and even though we're reducing revenues by producing less, we're going to lose less revenues than we are costs, and our profits are going to be higher. All right, and then finally, we could consider whether quantity 2 is an equilibrium. And what we notice here is that MR is equal to MC. So what does this look like on the graph? We notice that the slopes, and it kind of depends on how you draw it, if you've drawn it well, that the slopes at that quantity are exactly the same. And so in words, one more unit adds to revenue the same amount that it costs. That last unit of lemonade you produced cost 50 cents to make, and you sold it for 50 cents, or it brought in 50 cents of revenue. And so that represents kind of a stopping point. You're indifferent between producing it or not. And if you keep producing lemonade, your costs are going to grow and you're going to be making losses. So let's not go past that point. If I produce too little, however, I can make more revenue than it costs me to produce that lemonade, so let's keep on producing there. And so Q star gives us our first taste of what is kind of, this graph, gives us our first taste of what is the golden rule of profit maximization. So this is not an industry term, but I'm going to call it this. Firms choose quantity to maximize profits where MR equals MC. To find Q star, you're going to find where marginal revenue equals marginal cost. We're going to do this for all different types of firms, monopolies, competitive firms, and everything in between. And it all boils down to trying to maximize the distance between total revenues and total cost. And that's going to be at a place where marginal revenue equals marginal cost. We've shown it on the total cost and total revenue graphs. You can imagine the next place we're going is to our per unit graphs, where we have a little bit more flexibility in how we can study firms. And so that's that.